In order to make a nice clear ice cube for your drinks, it's important to consider quantum fields. First, boil the water to release dissolved gases, then make sure the freezing extends through the cube from a single surface. If the crystallization process starts from multiple nucleation points, then there'll be imperfections in the lattice structure when the regions of spreading ice meet, what we call topological defects. So, where do quantum fields come into all of this? Well, it turns out that the universe is a gigantic ice cube, and the imperfect freezing of its quantum fields right after the Big Bang very likely left vast topological defects stretching across the sky. These are cosmic strings, and many physicists think that they have to exist, and that we can find them. Reality has cracks in it. Universe-spanning filaments of ancient Big Bang energy formed from topological defects in the quantum fields, aka cosmic strings. They have subatomic thickness but prodigious mass, and they lash through space at close to the speed of light. They could be the most bizarre undiscovered entities that probably actually exist. To understand cosmic strings and to convince you that they probably do exist, we need to understand phase transitions in quantum fields. We need to see how a whole universe can freeze like a badly made ice cube. Heat up ice and it melts. Keep heating the water and it vaporizes. More heat still and that water vapor ionizes into plasma. But that's not the final phase transition. Keep heating until you hit temperatures of the extremely early universe, and a phase transition occurs in the quantum fields that underlie all particles. Just as with water, a field's inherent temperature massively changes its behavior. For example, the force-carrying field of the modern universe has a complicated structure. There are many different ways that it can vibrate. These modes manifest as different force-carrying particles moving in what we think of as separate force fields. This gives us our familiar electromagnetic strong and weak nuclear forces. But at very high temperatures, the complexities of the quantum fields sort of get ironed out. A little like how the complex crystal structure of ice dissolves when it melts. It seems pretty certain that in the first searing instant after the Big Bang, most of the modes of vibration of the quantum fields vanished. The many force-carrying fields behaved as a single field, generating a single master force. We know for sure that this is true for the electromagnetic and weak nuclear forces. We've re-merged those in our particle colliders. But it's almost certainly the case for the strong nuclear force and the Higgs field also. That's right, I said Higgs field. We think of the Higgs field and the Higgs boson as giving elementary particles their masses, but we should also think of the Higgs as a fifth fundamental force because it arises from the same field structure as the other non-gravity forces. And it's the freezing of this field that can give us our cosmic strings. Now, a quantum field is just some numerical property that the fabric of space can have. The field at any point can oscillate around that value, and those oscillations have quantized energy states. These vibrations can move through space, and we see them as particles. A field's numerical value is called its field strength, and it depends on the amount of energy in the field, sometimes in complex ways. In the absence of particles, a field will always drop to the nearest minimum in energy. This is the vacuum state of the field. In the early universe, the Higgs field had a very simple response to changes in energy, with a single minimum value, and even this vacuum state still contained a lot of energy. The shape of this so-called potential curve depends on the temperature. As the universe expanded and things cooled down, the Higgs field potential developed a bump. The lowest energy value was no longer a single number. Instead, new minima appeared around the old value. Actually, the Higgs field is really characterized by two numbers, a pair of field strengths, and so the new minimum formed a ring around the old minimum, resembling an item of festive Mexican headwear. So, quite suddenly, the Higgs field everywhere in the universe found itself sitting at a higher energy than it needed. It was momentarily stable at that point, just like a ball sitting at the top of a hill, but the slightest quantum jiggle would send the ball or the Higgs field rolling down in a random direction. And that's what happened. Here and there, across the universe, the Higgs field started falling towards the new vacuum state. We call this vacuum decay. Neighbouring points in a field drag on each other, pulling them towards the same value, just like how the magnetic dipoles in a ferromagnet drag each other into alignment. So, when this vacuum decay started at one point, the neighbouring points would have been dragged to the same part of the Higgs minimum. A bubble of this lower vacuum energy was nucleated, and it expanded at the speed of light. Many bubbles would have started at different places across the universe, and when the bubbles found each other, they merged. The old high-energy vacuum was completely erased. Or mostly erased. Just as with ice, topological defects should have formed where these bubbles met. Our ice cube forms sheets, but our Higgs field formed strings. Remember that the vacuum decayed in a random direction towards this circular valley. That means we can ascribe an angle to every point in that space, defining the relative value of the two components of the Higgs field. We'll call that the phase angle. Across a single expanding region of decaying vacuum, the phase angle would have been similar because these points were all pulled in the direction of the initial nucleation event. But independent bubbles may have very different phase angles. When bubbles met, the Higgs phase angle at the boundary tried to rotate to line up. This led to textures of slowly shifting phase angles across the universe. But if multiple bubbles join with different phase angles, then sometimes the lowest energy approach to lining up the phase angles is for them to vary smoothly around a loop, a 2π rotation of phase angle around the intersection. And that left a knot somewhere inside the loop where the fields couldn't align. The Higgs field at the centre of that knot was forced to take on the Higgs value at the top of the old potential hill rather than the valley. It became a fossil of the ancient high-energy vacuum that would persist into the modern universe. This sort of swirly topological defect is called a vortex, and we see 2D versions everywhere, from cyclones to swirls in the hair on your head. But in a 3D space, like, actual space, this sort of defect manifests as a cylindrical swirl around a central line, and that central line is our cosmic string. Other topological defects may have been possible. For example, a zero-dimensional point-like topological defect would be a magnetic monopole, and we talked about that recently. There are also ways to produce 2D defects called domain walls, but that's for another time. Okay, so we've managed to freeze the quantum field amidst the first ballings of the baby universe and woven some cosmic strings. What do they look like, and what do they do? Those phase angles really do prefer to line up, which means the loops around the defect tighten as much as they can. The filament of high vacuum energy is squeezed down to 1/10 trillionth the width of a proton, and yet it still holds an incredible amount of energy, which gives it the mass of the planet Mars for every 100 meters of length. And these things are long. They started as long as light can travel between the nucleation event and the completion of vacuum decay, and then the expanding universe stretched them up to the size of the observable universe. We actually expect multiple nucleation events in each causal horizon, potentially leading to dozens of cosmic strings in a network across the universe. Unlike the topological defects in ice, cosmic strings move and vibrate. They are also under some pretty insane tension, so vibrations travel along them at near the speed of light. This inevitably leads to collisions between segments of strings, either two distinct strings or two sections of the same string. When this happens, either the two segments pass straight through each other, or they switch partners, they intercommute. If a straight string collides with itself, it can cut out a loop. Then, if the loop intersects with itself again, it forms two smaller loops, chopping up into smaller and smaller pieces. But also, larger and larger loops keep forming from the original giant cosmic strings. Over time, the size of the largest loops increases, while at the same time populating the universe with their chopped up offspring. Once this intercommutation occurs, a pair of kinks is formed in each of the newly formed strings, and they speed away from each other along the string at near the speed of light. They're whipped back and forth by the oscillating string, and the incredible mass in these kinks causes them to radiate gravitational waves. In this way, cosmic strings shed energy, and so they slowly decay away. Eventually they vanish as the Higgs field smooths itself out across the filament. The smaller the loop size, the quicker they evaporate, so the breaking up of loops accelerates their demise. Okay, so that's what cosmic strings do. Now, how do we find them, assuming that they exist? Well, let's start with these gravitational waves. That radiation should be emitted in beams in the direction of oscillation of the string, so we might see flashes as these beams pass over our gravitational wave observatories. These are likely too weak to be seen at the current detectors such as LIGO, but future detectors such as LISA may be sensitive enough. Then there's the pulsar timing array. As we've described previously, it detects gravitational waves by looking for irregularities in the period of the fantastically regular flashes of light from pulsars. It also has the potential to spot the telltale signals from gravitationally radiating kinks in cosmic strings. The other way to spot cosmic strings also relies on a gravitational effect, gravitational lensing, which is the warping of background light sources due to the space-time warping effect of gravity. When a massive object sits between us and a distant light source, it bends all passing rays of light inwards, so focusing them towards us. We can see multiple images or even a ring surrounding that lens. A cosmic string would also deflect light towards itself, but that can only lead to a pair of split images, and that could potentially leave a chain of split images across the sky. No such chain has yet been detected, but upcoming gigantic all-sky surveys may give us the data that we need to find these. Now, if we do find a cosmic string, there's one other point of confusion that we need to settle. Is this a cosmic string, or is it a cosmic superstring? You've probably heard of string theory. We've certainly talked about it enough on this show. It's perhaps the most established candidate for a theory of everything, a theory that brings together all physics as we know it. The fundamental building blocks of string theory are the subatomic one-dimensional filaments called, fittingly, strings. The strings of string theory have nothing to do with the cosmic strings that I described. For one thing, they're ridiculously tiny instead of universe-sized. However, the universe may have found a way to confuse the two. Many physicists think that in the extremely early universe, the so-called inflationary epoch expanded the subatomic into the cosmic. Some of these string-theoretic strings may have been stretched to universe size by that event. Now those are called cosmic superstrings, and annoyingly they behave like regular cosmic strings in many ways, like the gravitational waves and the lensing, but there are differences. While cosmic strings almost always intercommute when they collide, cosmic superstrings are far more likely to pass straight through each other, which reduces the rate of chopping up into loops. They can also form junctions, specifically where two different types of superstring meet and combine to form a third connected string, which is in a sense a combination of the two. Now, this gives us a potential way to distinguish our cosmic string type. If one of these superstring junctions does any gravitational lensing, it should produce a 6-part image, perhaps with a parade of split pairs approaching it. Observation of such a junction would be the best, dare I say the only evidence to date in support of string theory. We should also expect cosmic superstrings to decay less quickly because they don't chop into loops as fast. That means they should result in a stronger gravitational wave background and possibly a distinct gravitational wave signature. Now, we haven't actually found cosmic strings or superstrings yet, but our searches have given us bounds on the range of allowed tensions and therefore energies of these things. And we have to keep looking. because it's very possible that the universe is riddled with veins of its primordial vacuum. If we can find one, who knows what we'll learn. We may discover truths about the origins of the universe, or the nature of quantum fields, or the validity of string theory. Many murky mysteries may become as clear as a well-made ice cube. I mean, what better way to see the inner workings of the universe than to find a crack in the fabric of space-time?
The following is a conversation with Konstantin Batygin, planetary astrophysicist at Caltech, interested in, among other things, the search for the distant, the mysterious Planet 9 in the outer regions of our solar system. Quick mention of our sponsors, Squarespace, Literati, Onnit, and NI. Check them out in the description to support this podcast. As a side note, let me say that our little sun is orbited by not just a few planets in the planetary region, but trillions of objects in the Kuiper Belt and the Oort cloud that extends over 3 light years out. This to me is amazing, since Proxima Centauri, the closest star to our sun, is only 4.2 light years away, and all of it is mostly covered in darkness. When I get a chance to go out swimming in the ocean, far from the shore, I'm sometimes overcome by the terrifying and the exciting feeling of not knowing what's there in the deep darkness. That's how I feel about the edge of our solar system. One day, I hope humans will travel there, or at the very least, AI systems that carry the flame of human consciousness. This is the Lex Friedman Podcast, and here's my conversation with Konstantin Batygin. What is Planet 9?
Planet 9 is an object that we believe lives in the solar system beyond the orbit of Neptune. It orbits the sun with a period of about 10,000 years and is about 5 Earth masses.
So that's a hypothesized object.
That's
There's
right.
some evidence for this kind of object. There's a bunch of different explanations. Can you give like an overview of the planets in our solar system? How many are there? What do we know and not know about them at a high level?
All right, that sounds like a good plan. So look, the solar system basically is comprised of 2 parts, the inner and the outer solar system. The inner solar system has the planets Mercury, Venus, Earth, and Mars. Now, Mercury is about 40% of the orbital separation of where the Earth is. It's closer to the sun. Venus is about 70%. Then Mars is about 160% further away from the sun than is the Earth. These planets that we, one of them we occupy, right, are pretty small. Okay, they're to leading order, sort of heavily overgrown asteroids, if you will. And this becomes evident when you move out further in the solar system and encounter Jupiter, which is 316 Earth masses, right, 10 times the size. And Saturn is another huge one. It's 90 Earth masses at about 10 times the separation from the sun as is the Earth. And then you have Uranus and Neptune at 20 and 30 respectively. For a long time, that is where the kind of massive part of the solar system ended. But what we've learned in the last 30 years is that beyond Neptune, there's this expansive field of icy debris, a second icy asteroid belt in the solar system. A lot of people have heard of the asteroid belt, which lives between Mars and Jupiter, right? Like that's a pretty common thing that people like to imagine and draw on lunchboxes and stuff. Mm-hmm. But beyond Neptune, there's a much more massive and much more radially expansive field of debris. Pluto, by the way, it belongs to that second, icy asteroid belt, which we call the Kuiper belt. It's just a big object within that population of bodies.
Pluto, the planet.
Pluto, the dwarf planet, the former planet,
Why is Pluto not a planet anymore?
I mean, it's tiny. We used to...
So size matters when it comes to planets.
100%. 100%. It's actually a fascinating story. When Pluto was discovered in 1930, the reason it was discovered in the first place is because astronomers at the time were looking for a 7 Earth mass planet somewhere beyond Neptune. Okay, it was hypothesized that such an object exists. When they found something, they interpreted that as a 7 Earth mass planet and immediately revised its mass downward because they couldn't resolve the object with the telescope. So it looked like just a point mass, star, rather than a physical disk. And they said, well, maybe it's not 7, maybe it's 1, right? And then sort of over the next, 40 years, Pluto's mass kept getting revised downwards until it was realized that it's like 500 times less massive than the Earth. Yeah. Right? I mean, like Pluto's surface area is almost perfectly equal to the surface area of Russia, actually. And Russia is big, but it's not a planet. Well, I mean, actually, we can touch more on that.
That's another discussion. So in some sense, earlier in the century, Pluto represented kind of our ignorance about the edges of the solar system. And perhaps Planet 9 is the thing that represents our ignorance about now, the modern set of ignorances about the edges of our solar system.
That's a good way to put it.
By the way, just imagining this belt of debris at the edge of our solar system is incredible.
Yeah.
Can you talk about it a little bit? What is the Kuiper belt, and what is the Oort cloud?
Yeah. Okay. So look, the simple way to think about it is that if you imagine, Neptune's orbit like a circle, right? Kind of maybe a factor of 1.3 times bigger on a radius of 1.3 times bigger. You've got a whole collection of icy objects. Most of these objects are sort of the size of Austin, maybe a little bit smaller. If you then zoom out, right, and explore the orbits of the most long period Kuiper belt objects. These are the things that have the biggest orbits and take the longest time to go around the sun. Then what you find is that beyond a critical orbit size, beyond a critical orbit period, which is about 4,000 years, you start to see weird structure. Like all the orbits sort of point into one direction. And all the orbits are kind of tilted in the same way by about 20 degrees with respect to the sun. This is particularly pronounced in orbits that are not heavily affected by Neptune. So there you start to see this weird dichotomy where there are objects which are stable, which Neptune does not mess with gravitationally, and unstable objects. The unstable objects are basically all over the place because they're being, kicked around by Neptune. The stable orbits show this remarkable pattern of clustering. We, back I guess 5 years ago, interpreted this pattern of clustering as a gravitational one-way sign of the existence of a planet in a distant planet, right? Something that is shepherding and confining these orbits together. Of course, right, you have to have some skepticism when you're talking about these things. You have to ask the question of, okay, how statistically significant is this clustering? And there are many authors that have indeed called that into question. We have done our own analyses, and basically, just like with all statistics, where there's kind of like multiple ways to do the exercise. You can either ask the question of, if I have a telescope that has surveyed this part of the sky, what are the chances that I would discover this clustering? That basically tells you that you have zero confidence, right? Like that does not give you a confident answer one way or another. Another way to do the statistics, which is what we prefer to do, is to say we have a whole night sky of discoveries in the Kuiper belt, right? And if we have some object over there, which has right ascension and declination, which is a way to say it's there on the sky, and it has some brightness, that means somebody looked over there and discovered an object was able to discover an object of that brightness or brighter. And through that analysis, you can construct a whole map on the sky of kind of where all of the surveys that have ever been done have collectively looked. So if you do the exercise this way, the false alarm probability of the clustering on which the Planet 9 hypothesis is built is about 0.4%.
Wow. Okay, so there's a million questions here. One, when you say bright objects, why are they bright? Are we talking about actual objects within the Kuiper Belt or the stuff we see through the Kuiper Belt?
This is the actual stuff we see in the Kuiper Belt. The way you go about discovering Kuiper Belt objects is pretty easy. I mean, it's easy in theory, right? Hard in practice.
Yeah.
All you do is you take snapshots of the sky, right? Choose that direction, say, and take, the high exposure snapshot. Then you wait a night and you do it again. And then you wait another night and you do it again. Objects that are just random stars in the galaxy don't move on the sky, whereas objects in the solar system will slowly move. This is no different than if you're driving down the freeway, it looks like, trees are going by you faster than the clouds, right? This is parallax. That's it. It's just they're reflecting light off of the sun and it's going back and hitting this.
There's a little bit of a glimmer from the different objects that you can see based on the reflection from the sun. So like there's actual light.
Yeah.
So it's not darkness.
That's right. These are just big icicles, basically, that are just reflecting sunlight back at you. It's then easy to understand why it's so hard to discover them, because light has to travel to, something like 40 times the distance between the Earth and the sun and then get reflected back.
Was that like an hour travel? Or
yeah, that's right. That's something like that, because the Earth to the sun is 8 minutes, I believe, and so
something,
yeah, hours.
in that order of magnitude. So that's interesting. So you have to like account for all of that, and then there's this huge amount of data, pixels that are coming from the pictures, and you have to integrate all of that together to paint a sort of like a high estimate of the different objects. Can you track them? Can you be like, that's Bob? Like, can you like?
Yes, exactly. In fact, one of them is named Joe Biden. Right? I mean, I'm not like, this is not even a joke, right?
Okay. Is there a Trump one or no?
No. I don't. Well,
not
actually,
yet.
I don't know. I haven't checked for that, but the way it works is if you discover one, you right away get a license plate for it. Okay, so like the first 4 numbers is the first year that this object has appeared on, in the data set, if you will. And then there's like this code that follows it, which basically tells you where in the sky it is, right? So one of the really interesting Kuiper Belt objects, which is very much part of the Planet 9 story, is called VP113. Because Joe Biden was vice president at the time, got nicknamed Biden.
VP 113, you said?
Yeah.
He got nicknamed Biden. Beautiful. What's the fingerprint for any particular object? Like, how do you know it's the same one?
Okay.
Or you just kind of like, from night to night, you take a picture. How do you know it's the same object?
Yeah, so the way you know is it appears in almost exactly the same part of the sky, except for moves by. And this is why actually you need at least 3 nights, because oftentimes asteroids, which are much closer to the Earth, will appear to move only slightly, but then on the 3rd night will move away. So that 3rd night is really there to detect acceleration. Now, the thing that I didn't really realize until, I started observing together with my partner in crime and all this, Mike Brown, is just the fact that for the first year when you make these detections, the only thing you really know with confidence is where it is on the night sky and how far away it is. Okay? That's it. You don't know anything about the orbit, because over 3 days, the object just moves so little. Right? That whole motion on the sky is entirely coming from motion of the Earth, right? So the Earth is kind of the car, the object is the tree, and you see it move.
Yeah.
So then to get some confident information about what its orbit looks like, you have to come back a year later, and then measure it again.
Oh, interesting. So do 3 nights, then come back a year later and do another 3 nights.
Yeah.
So you get the velocity, the acceleration from the 3 nights, and then you have the maybe
The additional
the additional information.
Because an orbit is basically described by 6 parameters. So you at least need 6 independent points, but in reality, you need many more observations to really pin down the orbit well.
And from that, you're able to construct for that one particular object an orbit. And then there's, of course, like how many objects are there?
There's like 4-ish thousand now.
But like in the future, there could be like millions.
Oh, sure. Oh, sure.
So
In fact, these things are hard to predict, but there's a new observatory called the Vera Rubin Observatory, which is coming online maybe next year. I mean, with COVID, these things are a little bit more uncertain, but they've actually been making great progress with construction. And so that telescope is just going to sort of scan the night sky every day automatically. And it's such an efficient survey that it might increase the census of the distant Kuiper belt, the things that I'm interested in, by a factor of 100. I mean, that would be really cool.
And that's an incredible.
They might just find Planet 9. Too. I mean, that's
like almost like literally pictures, like visually.
I mean, sure, yeah. Like the first detection you make, all you know is where it is in the sky and how far away it is. If something is, 500 times away from the sun, as far away from the sun as is the Earth, you know that's Planet 9. That's when the story concludes. And then you can study it.
Now you can study it, yeah. By the way, I'm going to use that as like, I don't know, a pickup line or a dating strategy. Like see the person for 3 days and then don't see them at all and then see them again in a year to determine the orbit, and over time.
¡Vamos allá! Esto es lo que soy. Es hora de la glotonería. ¡Vamos allá!